Let's begin by exploring what we mean when we talk about proof. In mathematics and logic, a proof is a logical argument that demonstrates the truth of a statement beyond any doubt. It's not just about convincing someone, it's about following a sequence of logical steps that anyone, given the same rules, would accept as valid. Proofs are the backbone of mathematics, ensuring that our conclusions are built on solid ground. But what exactly makes an argument a proof, and why are some arguments rejected? Let's dive deeper into these questions as we move forward. A valid proof follows a clear structure. It starts with assumptions or axioms, which are statements accepted as true without proof. From these, we use logical reasoning to derive new statements, step by step, until we reach the conclusion. Each step must be justified, either by a previously proven result, a definition, or a logical rule. This structure ensures that the proof is transparent and can be checked by others. If any step is unclear or unjustified, the proof may be questioned or even rejected. Understanding this structure is key to recognizing what counts as a proof. There are several accepted methods for constructing proofs. The most common is direct proof, where you start from known facts and use logical steps to reach your conclusion. Another is proof by contradiction, where you assume the opposite of what you want to prove and show that this leads to a contradiction. There's also proof by induction, often used for statements about natural numbers. Each method has its own rules and is accepted because it follows the logical structure required for a valid proof. Let's look at these methods in more detail. A direct proof is straightforward. You begin with known facts or assumptions and use logical steps to arrive at the statement you want to prove. Each step must be justified and the reasoning must be clear. For example, to prove that the sum of two even numbers is even, you start by defining even numbers and then show step by step how their sum fits the definition. Direct proofs are often the simplest and most intuitive, making them widely accepted in mathematics. Proof by contradiction is a powerful technique. Here, you assume the opposite of what you want to prove. If this assumption leads to a logical contradiction, then your original statement must be true. This method is especially useful when direct proof is difficult or impossible. For example, to prove that the square root of 2 is irrational, you assume it is rational and show that this leads to a contradiction. This approach is rigorous and widely accepted in mathematics. Proof by induction is commonly used for statements involving natural numbers. It has two main steps, the base case and the inductive step. First, you prove the statement for the smallest value, usually 1. Then, you assume it's true for some number k and prove it for k plus 1. If both steps succeed, the statement is true for all natural numbers. Induction is a cornerstone of mathematical reasoning and is accepted because it follows a clear, logical process. Sometimes, a picture really is worth 1,000 words. Visual proofs use diagrams or illustrations to demonstrate why a statement is true. These can be especially helpful for geometric problems, where seeing the relationships between shapes makes the logic clear. However, for a visual proof to be accepted, it must be precise and leave no room for ambiguity. If the diagram is unclear or doesn't cover all cases, the proof may be rejected. With advances in technology, some proofs are now assisted or even completed by computers. These proofs can handle vast amounts of data or check many cases quickly. A famous example is the proof of the four-color theorem, which relied on computer checking. While some mathematicians were initially skeptical, computer-assisted proofs are now generally accepted, provided the code and logic are transparent and can be independently verified. Not every argument is accepted as a proof. If a proof contains logical gaps, unjustified steps, or relies on assumptions that aren't universally accepted, it will likely be rejected. Even persuasive arguments or those that seem obvious can be dismissed if they don't follow the strict logical structure required. This ensures that only truly reliable results are accepted in mathematics and logic. Many proofs are rejected because of common mistakes. These include circular reasoning, where the conclusion is assumed in the argument, and overgeneralization, where a proof only works for specific cases but is claimed to be universal. Other pitfalls include missing steps, ambiguous language, or relying on intuition rather than logic. Being aware of these pitfalls helps in constructing solid, acceptable proofs. Precise definitions are crucial in proofs. If terms are not clearly defined, misunderstandings can arise, leading to incorrect conclusions. Mathematicians spend a lot of time making sure every term is unambiguous. This attention to detail ensures that everyone interprets the proof in the same way, reducing the risk of rejection due to confusion or misinterpretation. Every proof starts with some basic assumptions, called axioms. These are statements accepted as true without proof, forming the foundation of logical reasoning. If a proof relies on assumptions that are not accepted by the community, it may be rejected. That's why it's important to clearly state all assumptions at the beginning of a proof, ensuring everyone is on the same page. Rigor is what separates a valid proof from a mere argument. Every step must be justified, and the reasoning must be airtight. Mathematicians are trained to be skeptical and to question every detail. This rigorous approach ensures that proofs are reliable and that errors are caught before they become accepted as truth. Without rigor, the entire structure of mathematics would be at risk. Before a proof is widely accepted, it often undergoes peer review. Other mathematicians check the logic, look for errors, and ensure that every step is justified. This process helps catch mistakes and ensures that only valid proofs are published. Peer review is a cornerstone of the mathematical community, maintaining high standards and building trust in the results. What counts as a proof has changed over time. In ancient Greece, geometric proofs were often visual and less formal. Over the centuries, standards became more rigorous, with greater emphasis on logic and precision. Today, proofs must meet strict criteria to be accepted. This evolution reflects the growing complexity of mathematics and the need for absolute certainty in our conclusions. Throughout history, many proofs have been rejected, even by famous mathematicians. Sometimes, a proof is found to contain a subtle error or an unjustified assumption. For example, early attempts to prove Fermat's last theorem were rejected for lacking rigor. These cases highlight the importance of careful reasoning and the willingness to question even widely accepted ideas. A single counterexample can disprove a statement, no matter how convincing a proof may seem. If someone finds a case where the statement fails, the proof is invalid. This is why mathematicians are always on the lookout for counterexamples, testing the limits of their arguments, and ensuring that their proofs hold in every possible case. Intuitive arguments can be persuasive, but they are not the same as proofs. An intuition might suggest that a statement is true, but without a logical argument, it cannot be accepted as a proof. Mathematics values certainty over persuasion, and only logical, step-by-step reasoning is accepted as proof. Intuition can guide us, but it must be backed by logic. The language used in proofs is precise and unambiguous. Words like therefore, if and only if, and suppose have specific meanings. Ambiguous language can lead to misunderstandings and rejection. Mathematicians are careful to use language that leaves no doubt about the logic and structure of their arguments. While we often think of proofs in mathematics, the concept extends to other fields like law, science, and philosophy. Each field has its own standards for what counts as proof. In science, for example, proof often means strong evidence from experiments, while in law, it means convincing a judge or jury beyond reasonable doubt. Understanding these differences helps us appreciate the unique rigor of mathematical proof. Technology has changed the way we construct and check proofs. Computer programs can now verify long and complex proofs, catching errors that humans might miss. This has led to new types of proofs, like those generated by automated theorem provers. While some worry about relying too much on technology, most mathematicians see it as a valuable tool for ensuring accuracy and rigor. Despite advances in technology, humans still play a crucial role in creating and understanding proofs. Creativity, intuition, and insight are needed to come up with new ideas and approaches. Computers can check logic, but they can't replace the human spark that drives mathematical discovery. The best proofs combine rigorous logic with creative thinking. A proof is only useful if it can be communicated clearly to others. Mathematicians spend a lot of time writing and revising their proofs to make sure every step is understandable. Clear communication helps others verify the proof and builds confidence in the result. If a proof is hard to follow, it may be rejected even if it's logically correct. Learning to construct and understand proofs is a key part of mathematical education. Students are taught to follow logical steps, justify their reasoning, and avoid common pitfalls. This training develops critical thinking skills that are valuable far beyond mathematics. Mastering proofs is challenging, but it's essential for anyone who wants to understand or contribute to mathematics. Proofs are not just about checking what we already know, they're also tools for discovery. By exploring the logical consequences of assumptions, mathematicians uncover new truths and connections. Sometimes, the process of trying to prove something leads to unexpected insights or even new branches of mathematics. Proof is both a destination and a journey. Many great proofs are the result of collaboration. Mathematicians work together, sharing ideas and checking each other's work. Collaboration helps catch errors, refine arguments, and inspire new approaches. The mathematical community values openness and cooperation, recognizing that the best results often come from teamwork. Some mathematical problems remain unsolved for centuries, waiting for a proof. These open problems challenge mathematicians and drive progress in the field. When a proof is finally found, It's a major event, often leading to new questions and discoveries. The search for proofs is a never-ending adventure in mathematics. Once a proof is completed and checked, it's often published in a mathematical journal. Publication allows others to review, critique, and build upon the result. The process of publication is rigorous, ensuring that only high-quality proofs become part of the mathematical literature. This tradition maintains the integrity and reliability of mathematics. A mathematician's reputation often depends on the quality of their proofs. Publishing a new proof, especially for a famous problem, can bring recognition and respect. However, errors or rejected proofs can damage a reputation. This high standard motivates mathematicians to be thorough and careful in their work. Each new proof adds to the body of mathematical knowledge, building on what came before. Progress in mathematics is cumulative, with new results relying on earlier proofs. This interconnected web of knowledge is what makes mathematics so powerful and enduring. Every accepted proof is a step forward. The concept of proof raises deep philosophical questions. What does it mean for something to be true? Can we ever be absolutely certain? Philosophers and mathematicians have debated these questions for centuries. While mathematics strives for certainty, the philosophical foundations of proof remain a rich area of discussion. Creating a proof often requires as much creativity as solving a puzzle or composing music. Mathematicians look for clever insights, unexpected connections, and elegant arguments. The most beautiful proofs are celebrated for their simplicity and ingenuity. Creativity is at the heart of mathematical discovery. Simplicity is a hallmark of a great proof. The best proofs are not only correct, but also elegant and easy to understand. Mathematicians strive to find the simplest possible argument, avoiding unnecessary complexity. Simple proofs are easier to check, communicate, and build upon, making them especially valuable. A powerful proof often leads to generalizations, showing that a result holds in a broader context. Mathematicians look for patterns and connections that extend beyond the original problem. Generalization strengthens the impact of a proof and can open up new areas of research. Some proofs reveal results that are surprising or counterintuitive. These proofs challenge our assumptions and force us to rethink what we thought we knew. Counterintuitive results are often the most interesting, sparking debate and further investigation. Proofs give us the confidence to accept even the most surprising truths. Even the best mathematicians make mistakes. When errors are found in a proof, they are corrected through careful review and collaboration. This process strengthens the result and ensures that only accurate proofs are accepted. The willingness to find and fix errors is a sign of a healthy mathematical community. As mathematics evolves, so do our standards for proof. New fields, technologies, and ideas will continue to shape what counts as proof. The future may bring new methods, new challenges, and new ways of thinking about certainty and truth. What remains constant is the commitment to rigor, logic, and discovery. Proofs are not just for mathematicians. They play a role in public understanding of science, technology, and even everyday reasoning. Teaching the basics of logical proof helps people think critically, evaluate claims, and make better decisions. Proof is a tool for everyone, not just experts. Ethics play a role in the practice of proof. Mathematicians are expected to be honest about their results, acknowledge errors, and give credit to others. Plagiarism, or misrepresentation, can lead to rejection and loss of trust. Ethical standards help maintain the integrity of mathematics. Great proofs can be a source of inspiration, not just for mathematicians, but for anyone who values logic and creativity. The beauty and elegance of a well-crafted proof can spark curiosity and motivate others to explore new ideas. Proofs remind us of the power of human thought and the joy of discovery. There will always be statements that remain unproven, mysteries waiting to be solved. The search for proof is a journey into the unknown, pushing the boundaries of knowledge. Every new proof brings us closer to understanding the universe, but there will always be more to discover. Mathematics is a collaborative effort, with proofs serving as the common language. The community works together to check, refine, and build on each other's work. This spirit of cooperation ensures that mathematics continues to grow and thrive with proofs at its heart. The greatest proofs become part of the mathematical legacy, studied and admired for generations. They shape the way we think about mathematics and inspire future discoveries. The legacy of proof is a testament to the power of logic and the enduring quest for truth. To sum up, a proof is a logical argument that leaves no room for doubt. It must be clear, rigorous, and follow accepted methods. Proofs are checked, refined, and sometimes rejected if they fall short. The standards for proof ensure that mathematics remains a reliable and powerful tool for understanding the world. Whether accepted or rejected, every proof contributes to the ongoing story of discovery. The world of proofs is vast and fascinating. Whether you're a student, a professional, or just curious, exploring what counts as proof can deepen your understanding of logic, reasoning, and the nature of truth. Keep questioning, keep exploring, and remember that every great discovery begins with a single step toward proof.